Thank you very much, everybody, for coming today. It's my pleasure to introduce Bo-Wen Shen, one of our own. He's in the Math and Stats department. He's part of the Applied Math of department. So Bo-Wen comes from a very applied background. So he did his PhD in atmospheric science at NC State. And then he took on several research positions. For example, at Science Application International Corporation, SAIC, also at the ISIC, or Earth System Science Interdisciplinary Center in Maryland. And then he joined us in 2014. So I'm very happy to have you with us, Bo-Wen. And today, Bo-Wen is going to talk about the dual nature of chaos and order in weather and climate. I should say that Bo-Wen is really an expert in what in dynamic ecosystem goes into these Lorenz math, Lorenz equations, Lorenz attractors, and all that stuff. He's been working quite a bit on that, improving on models and finding new phenomenology on these models. So I'm really looking forward to hear your talk, Bo-Wen. Thanks for being here. The floor is yours.
Okay, thanks for your great introductions. And thanks for everyone attending this seminar. So it's my pleasure to be here. In the following, I'm going to give a presentation entitled On the Dual Nature of Chaos and Order in Weather and Climate. I'm going to provide new insights and opportunities within a generalized Lorenz model. Okay, here's the outline. I will first present you a revised view on the dual nature of chaos and order. Then I will discuss surface simulation to address our goal and approach. The revised view is proposed based on the recent finding using generalized Lorenz model. So therefore, here we are going to talk about major features of a generalized Lorenz model, including aggregated net feedback and also two kinds of attractor coexistence. After that, I'm going to introduce conceptual multiscale model. Actually, that was proposed first based on our global model simulation. And then now we can address the concept of this model using GLM, generalized model. In this part, I will focus on the alternative appearance of two kinds of attractor coexistence. And after that, we are going to present mathematical universality among non-dissipative Lorenz model, KDV, nonlinear Schrödinger equations, and the Pedlosky model. And near the end, I will briefly discuss new opportunity, especially for students, and give a summary. I personally enjoy scientific discussion very much, so your questions are very welcome. I prefer to discuss QA during QA section. However, on the other hand, during the presentation, if you think, okay, your questions can help you understand a little bit better, you can send the question through chat. I also have the window, okay, I can see. If the question is a little bit short, I can read it timely, then probably I can respond promptly as well. So this slide shows the so-called revised view on the dual nature of chaos and order. And that has been proposed based on our study during the past 10 years, okay? Both using global model and generalized Lorenz model. And the mathematical foundations for this has been published in several papers during the past years. Okay, for this particular paper entitled Is Weather Chaotic? Coexistence of Chaos and Order within a Generalized Lorenz Model. For this paper, which is submitted to BANS, here is Bulletin of American Meteorology Society, and here is for meteorology, not mathematics. For this paper, it has been reviewed for more than 2.5 years. Unfortunately, and finally, okay, this paper published last month. Okay, and one sentence summary is given here. By reviewing two kinds of attractor coexistence, we suggest that the entirety of weather possesses a dual nature of chaos and order with distinct predictability. From a perspective of a model prediction, we are interested in predictability. Okay? And the following two slides showing the milestone toward the revised view. In 2004, we deploy the highest resolution global weather and climate model. Yes, this model was developed as a unified system for climate and the weather study. Actually, the physical component and the land surface component of the model were derived from a climate model at NCAR. So therefore, at earlier time, we are very surprised the performance in weather predictions. And that's part of the reason I focus a lot of applications in weather predictions. And during that period, we obtained very interesting result at a time scale of 30 days. And that is kind of, area, is new areas. And our result has been published by AGU, American Geophysical Union Science Magazine, University of Maryland, and NASA as well, and also Dr. Endis of NCAR. He was a president at that time. And in 2011, I decided to work on Lorenz model to address the fundamental questions regarding the predictability. The math part was not challenging. I spent a couple of days deriving the 5-dimensional Lorenz model. However, for this paper, it took like 3 years to get published. Okay? And that published in 2014. And this paper has been reviewed by at least 9 reviewers and managed by 3 editors. And after 2011, I also led a research team develop so-called multiscale analysis package. We are looking for additional evidence showing the probability from observation. Okay? And I joined the San Diego State in 2014. During the first 3 years at San Diego, I continued my project, finished 10-year data analysis. Here, we're trying to looking for evidence from observation. I also continue to develop a high-dimensional Lorenz model, including 60, 70, 90. It may sound like funny, right? Okay, I do have my personal reason for doing this. And in this period, I also obtained kind of regular solutions, okay? And the last 3 years are more interesting and which are unforgettable, okay? We first completed the initial bench draft in summer 2017. And since then, that was 3 years ago, right? I provide bi-weekly updates through email among our co-authors. So I continue to keep updates what has been done in related studies, okay? And as mentioned earlier, okay, fortunately, our paper was published last month. It took like 3 years, okay? And during this period, I also finished my major paper, including Generalized Lorenz model that led to Attractor coexistence. I also finished a review article that, summarized the work with the Lorenz model and also global model. So today, we are going to focus on the results from these 2 studies. And during the past 2.5 years, during the review processes, in order to convince the reviewer, we finished a lot of versions and also complete more than 100-page responses, and including a list of a regular weather system. The first column indicates the name of a specific weather. The second column indicates the idealized solutions that share the similar dynamics. For example, I'd like to draw attention to the roll clouds, roll clouds. And a weather system can be shown below. This is a roll cloud. Earlier study showed that, roll clouds share dynamic similar to a solitary wave. And here is an idealized solutions of a solitary wave. And later we're going to show you the non-dissipative Lorenz model also have this type of solutions. Mathematically, that is a hypothetical square function. So here shows the 30-day simulation. From day 22 to day 30, our model simulated storm. We then plot its occasion as a function of time in rate on the left-hand side. And during the same as a real Hurricane Helene between September 12 and 24, we can plot its location as function of time in blue for comparison. Here shows horizontal shows longitude Vertical shows the latitude. This is in Atlantic Ocean. Their corresponding intensity are shown on the right-hand side. Horizontal and the vertical represent time and the minima sea level pressure. Hurricane is a storm with a low pressure in the center. The low pressure system is, the stronger the storm is. And during this period, you see there's a pressure drop. This indicates intensification of a hurricane. A comparison between the model in rate and observation in blue suggests that our model was able to simulate the rapid intensification. Okay. A comparison from these two slides, as well as analysis that will be discussed later, suggests that our model is able to simulate the hurricane at a time scale of 30 days. Okay. We published paper 10 years ago, and these results being reviewed in recent studies. Here shows another case showing 30-day simulations. This is a show, okay, MJO, a large scale weather systems. Okay. And based on these results, and as well as other results, we start thinking of the following two questions. From a perspective of weather prediction, we would like to understand under which condition global model have a scale at extended range time scale. Here we focus on 15 to 30 days. And then now community aware of this, that is called subseasonal, okay? And the second question, after we kind of developing the Lorenz model, we realize we need to address the second one, is whether chaotic. Since we are doing, personally doing science, okay, so therefore my personal view is that because we have observations, so therefore a research project should complete the following research cycle, including modeling observations and the theorizes, especially for people like me who are interested in theoretical studies. Okay. So today we are going to show you 30-day global model simulation. We will briefly mention about 10-year data analysis, looking for evidence from observation. Then we focus on a revised view on the dual nature of chaos and order, and based on a generalized Lorenz model. So specifically, in addition to attractor coexistence that lead to a duality, okay, we would like to show you two mechanisms that modulate or enable attractor coexistence. The first one is the so-called aggregated negative feedback, and the second one is time scale, large scale time vary forcing. Okay. So since we challenge the validity of the statement whether it's chaotic, yes, we challenge the statements. So therefore we need to define what is chaos. James Gleick published a book long time ago when I was a student in 1987. Okay, and it was a bestseller. After he published the book, there are many kind of journal and the new groups study this type of phenomena. In terms of content, okay, they also discuss the so-called butterfly effect in chapter 2, and actually that is a real chapter 1, right? And also many discuss the result from a study by Professor Lorenz at MIT in 1963. So simply speaking, okay, people accept chaos is about the butterfly effect. So the next question becomes, what is the butterfly effect? Historically, there are many studies trying to understand the origin of the term butterfly effect. Here, to simplify discussions, I simply present the view by Lorenz in 1993. He published a book, The Essence of Chaos. In this book, he mentioned butterfly effect in two places. First is in his figure two, okay? And this pattern appeared to like a butterfly wings. And later we're going to show you this pattern also similar to the solutions of his model in 1963. The second place he mentioned the butterfly effect is in the appendix with the same title. Okay. And actually this 72 This appendix actually includes his 72 conference presentation with a title given below near the bottom of this image. Predictability, does the flap of a butterfly wings set of a tornado in Texas? Okay. So as you can tell, this type of a butterfly effect is kind of well known in the community. However, here I'd like to draw attention, this conference presentation does not include any references, nor any mathematical equations. So therefore, it's very challenging to understand what is mechanism to support this type of a butterfly effect. In addition, in this conference presentation, the title actually was given by section chair Phillips Maurice. This title is not created by Lorenz. And based on our comprehensive literature review that has been performed during the past several years, I read a lot of studies, okay? And we suggest that actually these two butterfly effects are not the same. I'm going to explain a little bit in the next slides. We define the butterfly effect of a first kind as the follow. Okay? Sensitive dependence on initial condition. And this is well known in nonlinear dynamics, and which is also has been used to define chaos. And the following figure has been widely used to illustrate this feature. Here we basically compare control and the pair runs, and these two runs using the Lorenz model with the same parameter but different initial conditions. Here we simply add a tiny perturbation indicated by epsilon into the pair run. Epsilon is a small number that's equal to e to the negative 10. We then plot the solution, time evolution of these solutions as a function of time. In the horizontal axis, vertical represents amplitude. Initially, we only see one curve, right, which is in rate. And that means control run and the pair run produce almost identical results. And this indicates so-called continuous dependence on initial conditions. And that is the features of a nonlinear dynamic system, okay? Smooth nonlinear dynamic system. And later on, we do see two different curves, right, showing differences. And these differences are associated with tiny perturbation in the initial condition indicated by epsilon, right? So therefore, this feature is called sensitive dependence on initial conditions. We have abbreviation SDSU. And this is, okay, define the butterfly effect of the first kind, also define the chaos. We define the butterfly effect of the second kind as a metaphor that can enable, okay, indicates small perturbation can create a larger scale system. The major difference between these two is that B2 involve creations of a larger scale system, okay? And to me, this is different from this one. The first one is, say, initial tiny perturbation can have a huge impact on the time evolution of solutions. Okay? And the second one involves creations of a new system. So therefore, to simplify discussion, we focus on B1, and that is well known or accepted in the nonlinear dynamics. Okay. So of course, we still continue to publish paper for this type of butterfly effect. And for today, I know for the published paper in bands, we focus on B1. Here we introduce the Lorenz model, which consists of three first order ODE for three state variable X, Y, Z, and X, Y, Z represent amplitude of a Fourier mode for string function and the temperature. Okay. As we know, we can use X state variables as a coordinates to construct a phase space, right? So therefore, the dimension of the phase space for this case is 3. Okay. So therefore, we also refer the Lorenz model as 3-dimensional Lorenz model, 3D-LM. On the right-hand side, in addition to state variables, we have a 3 time-independent parameter, R, sigma, and D. Today, we focus on the impact of different R. R is Rayleigh number. And that is measure of the temperature difference between bottom and the top layer. The original Lorenz model dealing with so-called convection problem with heating from the low. So as a result, the R is also referred to as heating parameter because it's measure of temperature differences. Heating parameter, okay? So Lorenz model has two well-known nonlinear terms. We also analyze this nonlinear term, show that these two nonlinear terms form a nonlinear feedback loop. So the so-called generalized Lorenz model is derived based on the extensions of a nonlinear feedback loop. So within a Lorenz model, chaotic solutions has been a focus for several decades. In order to help some of you understand attractor coexistence, I'm going to show you other two types of solutions. Let RC here, critical values of a heating parameter for the onset of a chaos. RC can be determined analytically as 24.74. Okay. So here we present three cases with different value of R. And in each case, we compare control and the parallel run again. And the only difference between control and the parallel run is the initial timing perturbation indicated by epsilon. For the first case, R is less than RC. Okay. As you can tell, two run, control and the parallel run produce almost identical results, approaching a constant. This is called steady state solutions. When R is greater than RC, as discussed earlier, this represents chaotic solutions showing sensitive dependence on initial condition, also define butterfly effect of the first kind. Interestingly, when R is sufficiently large, the model produces nonlinear oscillatory signal, which is also known limit cycle solutions. I have additional slide to discuss this later. So simply based on the three cases, we found out chaotic solutions only within a finite ranges of a heating parameter. Again, chaotic solutions or butterfly effect of the first kinds appear within finite ranges of a heating parameter. The corresponding solution for two-dimensional phase space is shown on the top. For steady state, the solution appears as a point attractors. For chaotic, the solution appears as a tier number 8 in two-dimensional phase space. For periodic solutions, it becomes a closed in XY cross-sections, And the 3D trajectory of a chaotic orbit is shown here. We additionally add 3 2D cross-sections here. If we simply focus on XZ cross-section, you can tell this pattern similar to the figure 2 we discussed earlier, right? Okay. And partly because of the pattern, which is similar to butterfly wings. So therefore the term butterfly effect is used to indicate the features of SDIC, sensitive dependence on initial condition. Yes, partly because of the pattern that resemble a butterfly wings. So therefore the term butterfly effect is used to indicate the SDIC. The limit cycle solution can be understood a little bit better using these slides, especially on the top right. Here we present 200 orbits in different color during the time interval from tau from 1 to 10. Tau is non-dimensional time. We also plot these 200 orbits in black, during the last one time units from tau equal to 9 to 10. And through this representation, you can see how 200 orbits converge into a single orbit that represent the limit cycle solution. And this also indicates the so-called isolated feature natures. So therefore, limit cycle solution is defined as an isolated closed orbit. And through this representation, you can see limit cycle solution is not sensitive to initial condition. However, on the other hand, if among the 200 orbits, if we compare two of the orbits as function of time showing on the bottom left, we can see two orbits produce comparable amplitudes, right? And also comparable frequency. However, they do show differences in phase. As a result, when we compute differences showing on the bottom right, as a result of the phase, dependence of a phase initial condition, we observe oscillatory differences. If one of them is true value, so therefore we have oscillatory errors. We are going to use this to analyze our 30-day simulation. It was not easy for us to understand these features. I will explain a little bit later, okay? So for now, we already introduced 3 types of solutions within a Lorenz model, right? So we may ask, does butterfly effect always appear? So to address, okay, these problems using generalized Lorenz model, let me show you, okay, one animations for our global model. It's a kind of a delay, right, from your side, because I can tell, okay, it's a delay from my iPad. So probably I need to replay a little bit, okay? So this shows the so-called, it's not very clear from your side, I understand, okay? Anyway, this animation shows how initial shock dissipated. The initial shock is created due to the imbalance between the model and the data, or we say data simulation, okay? However, the model has mechanisms to dissipate the initial shock. So therefore, I hope you can agree with me, okay? The initial shock does not cause significant impact in the time evolutions of following simulations. Okay? So next week, we are going to discuss the generalized Lorenz model, which is shown on the right-hand side. And the original Lorenz model is discussed on the left-hand side for comparison. As discussed earlier, mentioned the Lorenz model is derived based on the extensions of a nonlinear feedback loop, as indicated by the circle. Okay? And the mathematical part has been published in several papers, so I'm not going to repeat the detail. Instead, I'm going to present the major features for GLM. The first one, it allows any up number modes. As a result, the original Lorenz model becomes a subset. And today we focus on aggregated negative feedback that enable 2 kinds of attractor coexistence. The first kind included steady state and a chaotic solution. The second kind include the limit cycle and the steady state solutions. We will discuss in a minute.
But when can I ask a quick question?
Sure. Yeah.
To put perspective, why are you adding more terms in the Lorenz model, and what is the importance of the physics behind including more terms in the model? Okay,
so that's showing here. First, for example, we can mimic it in a kind of a real situation as compared to high-dimensional global model. You see my point? Because previous people say nonlinearity causes chaotic behavior. So therefore, some of the people believe if we are going to higher dimensional global model, because nonlinearity becomes stronger and the system may become more chaotic and chaotic. Okay, then what's the point for development of a high dimensional model? That is original motivation. Okay, I'm sorry I cannot tell that kind of historical reasons in the beginning. And here provide a little bit information. So therefore that can help you to understand why this is important. The first column indicates the number of modes from 3, 5, 6 to 7. And the second column indicates the value of RC. RC again represent the critical values of a heating parameter for onset of a chaos. As discussed earlier, Lorenz model has RC of 2474. A comparison among 3D, 5D, 7D, 9D suggests high dimensional Lorenz model require larger heating parameter for the onset of a chaos. And this indicates aggregated net feedback. Why? Because in higher dimensional Lorenz model in our versions, the higher dimensional Lorenz model will include smaller scale modes. And these smaller scale modes may be associated with dissipative terms that provide the negative feedback to the system. More importantly, we derive in a way all kinds of negative feedback can be aggregated through nonlinearity. Yeah, yes, that is through nonlinearity, okay, to provide stronger dissipation. As a result, higher dimensional Lorenz model in our version becomes stable, more stable. And also because of this aggregated net feedback, okay, it also able to change the stability of unstable critical point to become stable. So therefore the system allow coexistence of stable and unstable critical points that lead to attractor coexistence, okay? I need to speed up a little bit, okay? The first kind of attractor coexistence is shown using these three cases, using generalized Lorenz model with 9 modes, okay? In these three cases, we use same model configurations, but different initial conditions. For example, we may put initial condition near the origin, that is trivial critical point, or we put initial condition close to non-trivial critical points. And in each case, we additional perform parallel run to understand the impact of timing perturbations, okay? So therefore, in each panel, we plot 2 runs. For the first 2 cases showing in the left and the middle panel, control and parallel run produce results that approach a constant, right? So these are steady state solutions. In the third case, control and parallel run produce almost identical result initially, but different result, and this is the chaotic orbit. We can also use the following approach using ensemble run to plot 250 orbits into a 2-dimensional phase space. And this figure really shows, okay, coexistence of chaotic orbits and the point attractors. And also we can tell they occupy different space. So therefore, from a perspective of machine learning, it's a good project for students to looking for decision boundary that can separate, okay, these 2 types of solutions. The decision boundary is close to the Bayesian boundary, okay? However, decision boundary allow tolerance, and that is a little bit easier for students, okay? So more detail regarding the approach using ensemble run are shown here. I'm going to skip the detail, okay? So instead, I focus on the implications. Consider right now we have 2 different kind of, here actually 3 kind of attractors, okay? So therefore, given an initial timing perturbation, if it is associated with a chaotic orbit, we know that it's going to have a huge impact in the time evolutions of a solution. On the other hand, if the initial timing perturbation is associated with steady state, we know it's going to have no impact, long-term impact at all. No long-term, it still have a short-term impact. As a result, a simple comparison between the 3D and the 9D LM. Here we focus on chaotic regions for 3D. First attractor coexistence for 9D, we can say butterfly effects always appear within 3D LM. However, butterfly effect may or may not appear within generalized Lorenz model. So therefore, we believe the generalized Lorenz model with attractor coexistence is more realistic. We may use the following as analogy again. Analogy means, okay, that can help us to understand. Okay. Consider an individual. He may make significant contribution in one society or environment. He may not able to do so in another environment. Okay. So we believe, okay, this is more realistic. The so-called second kind of coexistence is illustrated using this animation. Here we show 2048 orbits. At a given time, we only plot the trajectory between the current time and the last 1/4 time unit. Namely, at a given time, we only plot a small segment of a trajectory. So through this technique, we can see how some of orbits gradually converge into a single orbit, okay? And here, the first bullet gave us definitions of a limit cycle solution. So at this point, at this time, you can see the limit cycle solution is shown by the single orbit that has the largest spatial scale. And for the rest of our orbit, you can also see how they spiral into one of the point attractors. So therefore, this animation shows the second kind of attractor coexistence. So previously we show, okay, if two orbits that eventually converge to limit cycle solution as a result of a dependence of phase on initial condition, we observe oscillatory differences, right? Vertical axis represent differences. Here we have oscillatory differences. If one of them is true value, then we expect oscillatory errors. Now we are going to use this to analyze the 30-day simulations we present in the beginning. Around the represent time for the 30-day period. Vertical represent the correlation coefficients of the temperature against observation. So during the 30-day period, we observe the correlation coefficients are about 0.65. Okay. And in the community, it accepts if the coefficient are about 0.6, it's a good predictions. So therefore, this analysis provides additional support to our 30-day simulation presented in the beginning. However, I need to mention that back to 10 years ago, when we first see this type of a solution, we are not quite sure why it becomes oscillatory, especially if we simply focus on the divergence of a chaotic solution. We may interpret the error as a monotonic increase function. So then how come we have this type of oscillatory? And then right now, everything, especially during the past 2 to 3 years, everything becomes clear. Okay? So in the paper, we do provide additional analysis between these two cases. Then we suggest the realistic dimensions of Hurricane Helene from day 22 to day 30 becomes possible if we can obtain realistic of the following simulation. And this is more meteorology, and that is support these figures. Okay, back to 10 years ago, people still believe there's limits of predictability that is within 2 weeks. So that's why many people, he does not believe we can obtain simulations at a scale of 30 days. Okay? And here's a summary, okay, for people who like nonlinear dynamics, okay. Here we can simply provide a one-sentence summary between the difference between in the differences of a Lorenz model and general Lorenz model. I believe, okay, Ricardo is already known. That is, okay, for Lorenz model, it produces monostability. For general Lorenz model, that allow multi-stability. Simply speaking, within chaotic region, the Lorenz model only allow unstable critical points. For GLM, we allow coexistence of stable and unstable critical points. And this feature is, okay, enabled by the aggregated negative feedback. And for now, we only show the results with a time-independent parameter. Again, time-independent parameter. Next, we are going to show a scenario with time-varying heating function. And this provides more realistic scenario as compared to the real weather and the climate as well. Okay. So first, I am going to present you a conceptual multi-scale model that proposed in 2010 based on our global model simulations. As mentioned, we developed a model as a unified system for climate and weather study. Although we focus on applications of weather, however, we try to address a very generic questions regarding triple scale interaction. As we know that three-body problems is very challenging, right? Here is a triple scale interactions. If we focus on performance of tropical cyclones at the medium scale, we would like to understand the impact by the largest scale. Okay. And we have a term called through the downscaling process. We also would like to understand the impact from small scale process through so-called upscaling processes. And during the past, as mentioned, this conceptual model has been proposed more than 10 years. So when I present in earlier time, I often use the following as an analogy. And I also made a kind of mistake. I'm going to explain to you a little bit more. Okay. So say if we focus on performance of a department, I'm not saying math department for now, okay? The performance of a department, we would like to understand how strong support we can get from College of Science or school. And we also would like to receive a strong contribution from individual faculty, okay? So therefore, you can simply review modulation and the feedback. And actually, this conceptual model was proposed compared with the concept simply focus on butterfly effect. Okay. So during the past years, I also kind of published paper, and these are good paper to support this conceptual model. Okay. Here we focus on the modulation or the impact of a large scale wave. I select cases with different large scale wave, ER wave, MRG wave, arbitrary state wave, and here's MJO. Okay. However, at that time, we used the realistic model. So there were some people, if they believe theoretical understanding, they don't really trust this type of a result. So this slide provides additional scientific reason for why we focus on the impact of a large scale system. I'm going to skip for detail. Instead, I'm going to show you how we did and what has been done. We compare 30-day average with observation. We verify the simulations of a hurricane against, okay, arbitrary state jet and the multiple arbitrary state wave, okay? And all of this showing that our model was able to produce realistic simulations of environmental flow. Okay. So at this time, we show you realistic simulations of a hurricane at the medium scale. We show the realistic simulations of a large scale flow. The next question becomes how you assure the interactions among these two scales. So there was a period of time I lead a team to develop the tool called PMD. PMD stands for Parallel Ensemble Empirical Mode Decomposition. For now, I'm going to skip the details so you can simply view as kind of one kind of a Fourier transform. We are able to scale the tool up to 5,000 core, okay? So today we simply focus on the results. We know that, okay, using the Fourier transform, we extract the data into different wave modes, right? Okay. So here we simply compare two modes in green and in red. Okay. And the horizontal represent time, vertical represent amplitude. As you can tell, they have opposite tendency, showing one of them increase with time. This is associated with intensifications of a hurricane. So that means, okay, this one provide energy, okay, from the environmental flow to the hurricane, okay. We extend this type of analysis for a 10-year period. It's a labor-intensive work, okay? Okay. And it's not good for students to work on this type of work, okay? Because it's too labor-intensive. So I would like to provide additional evidence. Okay. Here, simply speaking, after 10 years, after 10 days, we are observed two twin TC, okay? One appear in the northern hemisphere, the other appear in the southern hemisphere. EQ indicate equator. These are called first pair of twin TC. This is called second pair of twin TC. So next, I simply present model performance in simulating these 4 TC. And later, I'm going to show you the impact of a large scale system on this twin TC. Actually, during the May 2002, there are 6, okay? So we simply focus on first 2 panels, okay? In the first panel, our focus is on the formations of a first twin TC. And light blue line indicate the observed track observation. And here animation shows our model simulation. As you can tell, model is able to simulate their formation and also subsequent movement. In the second panel, our focus is on the formations of a second pair of twin TC. Okay. In the third panel, first panel, we focus on super typhoon in West Pacific and the East hurricane in East Pacific. I'm going to skip it for now. Here, the previous TC is modulated by this system, okay? We studied from Indian Ocean. Okay. You can see this the system move eastward. Here is a conceptual model. We may view this as a movie cylinder. So we know that in the lee side, under certain conditions, we may observe a lee vortex, right? And this provide a potential mechanism for the formations of a twin TC we mentioned earlier. Okay? And this illustrates, okay, under this type of condition, we can extend the lead time of a TC predictions. Okay, and the next, I'm going to use the Generalized Lorenz model to illustrate this type of a modulation. Okay. Again, here we use time-varying heating function. Simply speaking, we use this heating function, which is a sine function that gave us interval between 10 to 350. Within this region, we expect chaotic steady state and limit cycle solution will appear. First panel shows the three trajectory. Start with similar initial conditions with tiny perturbation in the initial conditions. Second panel indicate the time evolutions of a heating function. Okay, and for the rest of a panel, we only very short period of time and showing how solution become diverged, and this indicate SDSU, right? And later they becomes chaotic. And since the heating is continue to increase, so once it becomes very large, we observe limit cycle solutions. Here shows the transition from chaotic orbit to limit cycle solutions during this cycle, okay? And for another cycle, we observe limit cycle solution again. We can apply the similar approach to generalized Lorenz model as well. And this is interesting. I'm going to skip for now, okay? This is for generalized Lorenz model. So again, first panel shows the trajectory start, okay, very closely. And we first observe chaotic solutions. Then we observe first kind of attractor coexistence. For example, here we do have a chaotic orbit. On the other hand, we have a kind of a steady state. Here's the non-zero, okay, solutions, okay, which is close to a kind of a constant. However, if we plot a long time period, we can see this type of solutions are kind of associated with the variations of heating. Okay. And then we observe the second kind of attractor coexistence. And this solution is interesting, that is related to climates, okay? So for now, let me skip. So simply learn from this slide, it shows alternative and the concurrent appearance of various type of solutions. Since we focus on duality, we also obtain regular solutions from various type of Lorenz model. Here we compare non-dissipative Lorenz model with Duffy equations. Yeah, here, left column indicate, first column indicate the non-dissipative Lorenz model. Right-hand side put the other physical systems. Here we compare Lorenz model with nonlinear Schrodinger. Here is okay, Z components for X for Lorenz model with KdV. On the right-hand side, we show the KdV in traveling wave coordinates. Okay. As discussed earlier, this type of raw clouds share dynamics similar to oscillatory wave, and mathematical oscillatory wave is represented by hyperbolic secant square functions. We also compare the Lorenz model with the Pedlosky model. If you are interested in math, if you are interested in earth science, this book, okay, the book by him is highly recommended. And these two models originate from very different PDE, partial differential equations. However, they can obtain ODE that are mathematically identical if we choose parameter. Okay. property. And I already checked with Pedlosky regarding these results during the summertime. And using our high-dimensional model, we can produce quasi-periodic flow. And here we want to emphasize that the quasi-periodicity in our model was created by mode-mode interactions, which is different from many other studies. Okay. Here's a list of a potential project for students. I'm going to skip for now. So let me give a conclusion. Okay. We have developed a generalized Lorenz model with the major feature of two kinds of attractor coexistence. Butterfly effect does not always appear. The two kinds of attractor coexistence are enabled or modulated by the aggregated negative feedback and the large time varying function heating. Based on this result, we propose a revised view on the dual nature of chaos and order in the weather and the climate. Simply speaking, we challenge the validity of the statement whether it's chaotic. So the revised view, okay, is neither too optimistic nor pessimistic as compared to Laplacian's view and the Lorentz view. And potentially, you can unify our theoretical understanding of probability using theoretical model and promising simulations using global model, especially recent model shows the probability over 2 weeks. We believe that the revised view with our past, current, and the future efforts may lead to paradigm shift in probability study, which suggests that effective detection and the classifications of a chaotic and the non-chaotic orbits can help extend the time of weather predictions. Future work will focus on the detections of non-oscillatory signal and also improve their simulations within the real-world climate model. Here's a selected references. Okay. Thanks for attention. So we started a little bit 5 minutes later, right? I do keep my promise. I reserve about 10 minutes for discussions. Thank you.
Thank you very much, Bo-Wen.
Yes.
And I'll open the floor for questions. If you want to ask a question, do not forget to unmute yourself and then ask the question.
I have a question from the student. He is very good. Okay, I really enjoyed the question from this student. Okay, I appreciate it. So the question is, did you use time vary heating function for study the period? Okay, for global model, the heating function is a function of time. For example, we have a solar radiation, blah, blah, blah. So therefore, simply speaking, original Lorenz model, if we use time independent parameter, that one is not very good to explain the real weather predictions, okay? So that's also why we start, okay, looking for the kind of a generalized Lorenz model and with different configurations, okay?
Hey, I don't know if you're supposed to ask questions via chat or something, but
go ahead, John. Just ask your question.
No problem. Yeah, I appreciate any kind of a problem questions. Okay.
So what you did was you showed a simulation of tropical cyclone formation, which means that you're interested in weather. And I guess the first question is, what happens if you restart your simulation? In other words, because in the middle of the simulation, every 3 hours, you have updates from, well, essentially every airplane, every commercial airliner in the planet, and they're taking temperature and possibly pressure measurements. And then you're getting a huge amount of data from weather sensors, at least in the developed world. And every time you, one problem is that you have to worry about what happens when you restart any type of numerical weather prediction model.
Okay.
You know, the normal ones, NavGem and all the others and stuff. So coamps for the lower models, and I'm just talking about atmospherics.
Okay.
you guys do a lot of coastal modeling and stuff. So I'm just kind of curious.
Okay, so what are your questions regarding so-called data simulation? Okay, data simulation normally they may have a so-called 6-hour updates because they keep observe the real situation and then put into the systems. So from a kind of a model perspective, it means we have a continuous initial conditions at a different time. However, for this type of work, we always compare the result at the same initial condition. Or, no, I should say the initial condition at the same time, We may change the model configuration. However, the initial condition, for example, if we start at September 1st, we always compare the different cases, control and the parallel runs study at the same time, So for different hurricanes, we can compare, for example, with a different initial condition, but we still also compare with the same time, So therefore, in other words, we always, when we say verifications, we verify the simulations, model simulation. For example, we will compare we perform 10-day simulation starting from September 1st. So therefore, after 10 days simulation, we have data from September 1st to September 11, right? And during the same period, we have observation. Then we compare with the observation.
Okay, how's it?
Excuse me. Let me interject here. Is that the question that John was asking is basically called data simulation. Are you able to incorporate real-time data into your simulation? That is the...
When I work for NASA, we work, our office is called Data Simulation Office, We have about 150 employees. And then for modeling group, we only have like 10 people. For modeling, we focus on model. Specifically, we can say we focus on the dynamic systems of the model, namely the equations. We don't dealing with the data simulation. Data simulation has been done by a very big group, and they focus on that. So therefore, I only have a model, a version of a model. I don't have a data simulation.
Okay, thanks.
Well, my real question is that because you this is chaos, and once you restart simulations every 3 or 6 hours, you have to account for that by creating a probability distribution function.
May I interrupt first? Probably I did not explain clear. Although you have update initial conditions at a different time, right? So however, when we rerun the cases, we still use the same initial condition at that time, because, for example, if we redo the case, that is start on September 1st, the new initial condition is not counted because that already changed the time of the data. We can only use the data correct by September 1st, and that is called initial condition. For data simulation, they don't have this type of problem. For data simulation, we simply view as kind of a 6-hour prediction system. Because data simulation performs 6 hours to obtain so-called initial case, then they merge the observation, correct at that time. So therefore, data simulations only view as a prediction system for 6 hour, prediction. Or we focus on so-called weather prediction. Once we are giving initial condition during the entire integrations, we cannot change the initial condition. We cannot. That is called predictions. So therefore, it's fundamentally different from data simulation system. Data simulation system allow you change, you update initial case every 6 hours. For real prediction, we don't. So therefore, people also call this as a free run.
Excuse me.
You cannot update your initial.
Hey, Bo-Wen.
Yes.
I think that Bryce had a question.
Yeah, I do. Thank you for that. There was something that was really interesting when you were describing the second attractor the video. Can you go back to that slide really quick? I think you had 2 point attractors and a chaotic attractor.
So can you kind of help me out?
It's before slide 29. Sorry.
Before slide 29, okay. So I'm going to. 29? 29 is here.
Yeah, so there are 2 point attractors, right? On the picture
on the right hand side?
Yeah.
Actually, there are 3 because we have a 2-point attractors. We have 2 type of attractors, but 3 attractors.
Okay.
Yeah.
Is there a way to describe a center of an attractor?
Oh yeah, that is a stable critical point.
Right. And then are we able to measure the distance between the attractors as well? So then yes, right?
Because within the generalized model, we can determine the unstable critical point. So therefore, this point can be determined okay, as a closed solutions, closed solution. Okay.
Yeah.
So
yeah, but Bryce, you can always define distance between sets of points. But what is your question about the distance between the attractors?
It's actually for my research because I wanted to use n-scroll attractors or chaotic attractors and place them arbitrarily far apart or specific distances apart to encode information. And this was actually exactly what I needed to ask. So.
Right, so there are standards way to just measure distance. I mean, there is no a distance. There are just many type of distances that you can define between sets of points. So just check for definition of a distance between sets of points, and then you will be able to get it in different ways. I had a question, Bo-Wen, since Bryce pointed to exactly this picture. You were mentioning that with artificial intelligence, you will be able to find the separatrix between the basin of attractions of the point attractors and the chaotic attractors. Wouldn't it be easier and shouldn't it coincide with an unstable limit cycle that separates? So usually unstable limit cycles are the separatrices between different type of dynamics. So I don't think that you need an AI here. You just need some sort of shooting method to find what is this unstable periodic orbit between these 2 attractors.
Yeah, thanks for your comments. Yeah, I need to share with you a little bit about my philosophy. Okay, so my view for example, for the math part, actually, I don't. Sorry for saying the following. Okay, actually, I encourage students to work on something which is a hard area. Simply speaking, for this one, the reason, okay, I suggest students to apply machine learning, because once you use machine learning to analyze this, so he has a skill in machine learning, okay. So that will be probably, from my perspective, that will be easier for him to find a job. That's my philosophy. For many other maths, I understand there's a way to compute. Okay. And also, if I do have a slide showing how we use so-called kernel PCA to find the boundary. Actually, it's not too challenging. Once they know SVD, singular value decomposition, however, that takes time. Okay. Once they understand, they can easily analyze this type of decision boundary. Okay. That's my philosophy. Okay. Because
yeah, I think you could even marry your philosophy with what I'm saying. So instead of finding the unstable periodic orbit using a shooting or Newton method, you can even use machine learning. But to put into context, it doesn't matter how you find the object. I think the object that you're after is an unstable periodic orbit. But I think. But in any case, we can discuss this offline, Bo-Wen, since we chat offline. I don't want to just take up all the questions. Are there any other questions from the audience at this stage?
Yeah, I just wanted to say that I think this is very interesting because when you do weather predictions and stuff like cyclones or something, anything that's going to predict in the future, you have to worry about the systems destabling, you know, as you restart the simulation, and any type of well, there's a lot of overhead. There's a lot of supercomputer power being, you know, is just a lot of CPU cycles. And if you can try and figure out how to stabilize, if you can decide how to, let's just say, a better way to stabilize the, you know, the primitive equations and stuff like that, not just the 850 hectopascals, but, you know, the others and the temperature and pressure and stuff like that. I think it would be really interesting. So I think that's, I just thought I'd let you know that I do appreciate these things.
Okay.
So.
All right, John, I encourage you to get in touch with Bo-Wen if you want to keep on the discussion. But at this point, I'd like to just close up because people have been here already for a while. And I would like to thank again Bo-Wen for this nice presentation and showing us what he's doing. And anybody that is interested in Bo-Wen's research, he's always, I know that he's always welcoming students in his lab. So just get in touch with him. Thank you very much, Bo-Wen.
Yeah, thank you very much. Yeah.
Thank you, everybody, for attending the talk, and thank you, Bo-Wen, for a very interesting presentation.
Thank you very much.